I would like to present today the results of our study that has been recently published, and I will also show some preliminary new results shortly. Um, and at this point, I already want to thank my colleagues, my co-authors, mainly Axel and Dennis, for being such a great team here, and all my other colleagues, of course. Yeah, so quickly my agenda of this talk. So I will present some overview of the background, some basic things about speleothems and the Laacher See eruption. I will present our results, also and also the more recent results, and then go over to the implications on the potential environmental and the climatic impacts of the eruption. So speleothems. So for those in the audience who don't know so much about speleothems, speleothems are carbonate deposits that form in caves when groundwater percolates through limestone and then precipitates inside the caves. And these calcite layers, they include climatic signals. So the protected cave environment minimize post-depositional alterations. So we have so in the speleothems, a lot of isotopic and chemical proxies are preserved, and these contain fingerprints of rainfall, temperature, or atmospheric circulation. Caves or speleothems are found, as I said, in karst caves, and karst regions are found across a large range of climate zones, from the tropics all above to Greenland. We find karst caves and also speleothem records, so we have a very broad distribution across the globe. Speleothems can have very high growth rates, so we can even have annual laminations or annual growth bands that may allow reconstructions of seasonal variability. And then lastly, we have the technique of uranium series dating or thorium-uranium dating that allows absolute and precise chronologies up to the per mil range and uncertainties. And we can date speleothems from basically 0 to an age of 500 to 600 kiloyears old. And as I said, we have a large variety of proxies that can be analyzed or are preserved in speleothems. So these are quite nice advantages that are unmatched by many surface archives, especially the dating, the absolute dating potential. And speleothems can also be archives of past volcanism. So volcanic, so here you see this nice scheme of Alice Payne et al., where you can see that volcanic material from an eruption can be transported either directly into the cave via aeolian transport and then deposited in the cave or above the stalagmite. But also, of course, we can have a leaching of trace elements or colloidal or colloids or particulates that are leached from the tephra above the cave and then percolate through the karst zone and are then transported into the speleothem through the drip water. And indeed, we are not the first who have been doing this. So there have been quite a few studies that showed that speleothems can record volcanic eruptions through different ways, different methods. So either by sulfur signals or by trace element spikes. So in this study, we asked questions if we can use speleothems to date volcanic eruptions. So far, this hasn't been done so extensively. So most of the time when people have found a volcanic spike, it was more or less coincidence or not very clear signals. And we thought, can we use the big advantage of speleothems to date their dating potential to date a single volcanic eruption? And for this, we selected the Laacher See Eruption. What is the Laacher See Eruption? So it is the largest volcanic event in Central Europe during the Quaternary. So the Laacher See Eruption, what you see here, it's now the caldera of this eruption. The Laacher See volcano erupted in the East Eifel volcanic field in Western Germany. Here you see Germany. Here's the Eifel volcanic field and the approximate location of the Laacher See volcano. You see also the ash dispersal, the most dominant ash dispersal plumes. So the eruption size is probably comparable to Mount Pinatubo in 1991, where we know that it cooled the Earth climate and by a few degrees Celsius in the following years. And for the Laacher See eruption, we know that it had an enormous impact on the Central European environment. So there were pyroclastic flows that traveled into the Rhine Valley. So here you see a close-up now. Here's the Rhine Valley, so a big river system in Central Europe. So the pyroclastic flows created a temporary dam in this area, and this created a large temporary lake. And when the dam collapsed, there were really large flood wave deposited materials about 10 meters above the normal river level. So there are some pictures of trace dams in these deposits that shouldn't be there without this flood wave. Also, there's some evidence for cultural impact, so that people who were living in that area left Central Germany in the few hundred years after the eruption. So, which is, I would say, no surprise if you imagine that the ash deposits were several centimeters or meters here close to the Laacher See, and then several centimeters in Central Germany. So it must have looked like this roughly in that area. So not very nice to live there. So, but still, the climatic impact is still more or less uncertain of the Laacher See eruption. This is because so far no direct evidence has been found in Greenland ice cores, despite intensive search efforts. Here's an example by Abbott et al., where they defined several candidate events of different size, different volcanic sulfur deposition rates, so big, and these candidates event include a very large eruption, but also several smaller size. So the stratospheric sulfur injection rate is very uncertain, and with this, it's also uncertain if the eruption had a big or small climatic impact. Yes, and why is the eruption still important? So the Laacher See tephra LST is a very important time marker in many Central European paleoclimatic archives. So due to this wide dispersal of the tephra, the fallout has been found in many different lake sediments, and this is why the tephra is being used to synchronize and to cross date different sedimentary archives. So, and this makes it very important to have a precise and accurate age for the eruption. And of course, there have been many dating efforts to get such an age. So, for example, there was an argon dating. People have tried early in the 1990s, of course, to date the tephra by argon, but this age has still a very large uncertainty of several hundred years. Then, in 1999, Brauer et al. Got a very precise age of the Laacher See tephra obtained by WAF counting in the Meerfelder Maar record. Then many studies also use C14-based method, either by dating organic material buried by the tephra, dating sediment cores by C14, and then interpolating the age to the tephra layer, or using C14 tree ring chronology. So the C14 community, please excuse me plotting all these different ages together in one graph, because of course it's not so straightforward to compare these all with each other, because also the C14 calibration curve has a plateau in exactly that time frame. So the errors get quite large. And also the different INTCAL versions, therefore they changed a bit in that time period. So this is still INTCAL 9 dates and INTCAL 13 dates. So but what I want to highlight here, that even though there are many dates available that do more or less agree with each other, or maybe some not, but there may be explanations for that. It was, of course, the Meerfelder Maar date that has become more or less the age that the community agreed on, and that was used since then, because it's, of course, a very precise. The Meerfelder Maar has a very good age control with the WAF counting. So this was challenged in 21 when Reinig et al. Redated the eruption by using annual radiocarbon records from several carbonized fossil trees. So they used these radiocarbon chronologies to wiggle match it with the radiocarbon calibration curve, which they got this very precise age of the Laacher See eruption, which indicated that it was around 200 years earlier than assumed from the previous age. And with this late glacial age, this new C14 date supported a late glacial age of the Laacher See eruption, and with this age, Reinig et al. Also claimed that this would synchronize Central European records at the Belling-Allerød-Younger Dryas transition, and that the climate change in Central Europe and in Greenland would be also synchronous. So while this date more or less synchronized at least the Central European records, there are still some open questions. So it was debated, or it was questions if the C14 age by Reinig et al. Could have been too old due to magmatic old CO2 in the trees. And on the other hand, the Laacher See eruption is also not yet identified in the Greenland ice cores, so it's not yet possible to reliably assess the relative timing in Greenland and Europe. And with all this, the climatic impact is still not really resolved. So we asked the question if we could use the Speleothem theme to solve this question, if we can determine an independent age for the Laacher See by using uranium-thorium dating and to assess the regional and or global climatic impact. For this, we selected a sample from Herbstlabyrinth cave in Hessen, which is located about 40 kilometers east of the Laacher See volcano, which you can see here. So it's directly in the eastern fallout lobe of the eruption, and inside of the cave were even volcanic deposits found inside the cave, so it was the ideal site to look for the eruption in a speleothem. And in addition, so there was some really extensive monitoring and other studies going on by the group of Dennis Scholz in Mainz in Herbstlabyrinth cave. So there was a few years of monitoring of drip waters in the cave. And for example, Simon Michel, the PhD student at the time, found out that the drip water and Speleothem delta 18O values show a close link to North Atlantic climate change, and that the oxygen isotopes also seem to have some temperature control. And in this project, there was also a stalagmite studied. So this is stalagmite HLK2 that was growing over the Holocene. So here you see the past 14,000 years, and in black the oxygen isotope record of HLK2. And you can indeed see this that the relationship to the North Crypt oxygen isotope record is quite close. So they share a lot of similar features, and most importantly, we knew that the Speleothem covered the transition from the Bölling-Allerød to the Younger Dryas period. So this is about here, this piece of the stalagmite. So we aim to improve the age model with new thorium-uranium dates to get a better precision. We had laser ablation, ICP-MS, to get high resolution trace element records to measure potentially ash-leached elements. In addition, we did fluorescence microscopy, and because we knew that the Speleothem was very slow growing, we analyzed the oxygen isotopes by using the Heidelberg ion probe, which allowed a really high resolution in the oxygen isotopes, and also a high sensitivity for the sulfur contents. So with this, we got a near annually resolved record, which was very nice to have and to really see how the volcanic spike would look like. With this, we jump directly to results. So this is what we got from the sulfur analysis. So here you see a beautiful and abrupt strong sulfur spike, both measured with the ion probe and laser ablation, ICP-MS. And here on the other side, you see some APMA and ion probe maps around that area that also confirm this really abrupt increase of sulfur contents along this growth layer of the stalagmite. As I said, we also did fluorescence microscopy. So you may have already seen this before in the other pictures. So you see that this jump in the sulfur contents is also associated with the very distinct horizon of fluorescent material. So you see this bright greenish color here at this horizon. So that is all fluorescent or fluorescent matter. Yeah. So, and then we measured also laser. With the laser, as I said, we measured a large range of potentially ash or tephra leached elements. And we saw, for example, in sodium, uranium, and barium, we saw a very sharp peak as well, so coinciding with the sulfur spike. And we know that the tephra of the Laacher See eruption was enriched also in these soluble elements. So all in all, we can say that we see a clear geochemical fingerprint of a proximal volcanic eruption, and yeah, this is the Laacher See eruption. To date this eruption or this spike in the Speleothem, as I said, that we tried to improve the age model. So here you can see our results from thorium uranium dating. You see the age over distance from top, and here at this depth you see where we identified the volcanic spike. So these filled symbols are the new ages that we obtained with a better precision, with a more state-of-the-art instrument. And I hope you can see this orange line here, which is the age model that we obtained from annual layer counting, because in the Speleothem, under the fluorescence microscopy, we see these beautiful annual layers, and we can count these annual layers, and they suggest a very constant growth rate, so a near linear growth, and especially at that around that period where we have the volcanic spike. And by combining the layer counting and the uranium thorium dates, we obtained a uranium thorium age of 13,049 plus minus 30 years. Which basically confirms a late glacial age of the Laacher See eruption, as previously suggested by Reinig et al. We can compare this as well. So with the other ages that before, so with the plot that I have been showing before. So in here you can see that the age, while our age is a little bit at the older tail of these ages. So we agree with most of the C14 base records, and for the, I mean, I mentioned that many of these are calibrated to other INTCAL curves. So at least for these where I got the C14 ages, I recalibrated the data. So for these where I was more or less sure that we can do this. So for these, it seems to fit quite well together when we do a recalibration of these older C14 based ages. So all in all, I think that our date confirms a late glacial age of the Laacher See eruption. And this will be now the next part of the talk. So I promised to talk about what our results mean for the environmental impact of the Laacher See eruption, because we have, of course, the eruption as well as potential climatic and environmental proxies in the Speleothem record. So here you see a number of proxies, so mainly trace elements, but also oxygen isotopes here. I will guide you through that very busy plot. So here in this area, we have again the volcanic spike and the fluorescence here, and then the sulfur. And as I said, we have this abruptly increasing peak in fluorescence and potentially in degraded organic matter, and also in these tephra-derived trace elements. And these occur within a few weeks or months after the Laacher See eruption. And we interpret this, of course, as to a result from the strong destruction of the vegetation above the cave, and then the degradation and mobilization of these organic matter, and then a direct transport after the eruption. But we also see in the decades, in 20 to 30 years after the eruption, we see a smooth second peak in barium, uranium, and sodium mainly, which we think may indicate a change to more oxidizing environment in the soil due to a decrease in soil pH after the eruption, which may then, so a lower pH may promote the mobilization of water soluble elements, or it can also enhance the cation exchange with clay minerals in the soil. So we think that this secondary peak is a reflection of changed soil conditions, or the impact of the tephra on the soil conditions. And what we found very interesting was that we do not really find a clear response of potential climatic proxies, so magnesium or strontium in speleothems are often indicators of hydroclimatic changes, but we do not really see a clear picture here. So it's very noisy before and after and during the eruption. We also don't see a clear response of growth rate. So this is the lamina, the thickness of the counted lamina, and also in the oxygen isotopes, where there's not really a clear signal, maybe a slight drop here. And this slight drop led us to do some more analysis. So now come more so for unpublished results. So we thought that maybe we have missed a peak in oxygen isotopes. Maybe our profile is not representative. So what my colleague Axel Schmidt did in the last few months was to analyze several profiles of the oxygen isotopes by using the ion probe. So he measured 5 and another 5 profiles in the 10 to 20 years before and after the eruption. And he correlated this with the annual layer counts and got these average curves. So these are 2 average curves for 5 profiles each, and these are in the highest resolution that we could get. So it's 10 micrometer resolution, so about 1 to 2 samples at least per year. And yeah, what we can say from this analysis, that there may be a reproducible decrease in oxygen isotopes by about 0.5 per mil in the 1 or 2 years after the eruption. So that is reproducible in all the profiles. You can see this here by this light bluer colors here in all the profiles. So this is in all the profiles, but it is a very small signal. So as I said previously, the oxygen isotope at the site of Herbstlabrand Cave have been connected to temperature, but it's very hard to use this calibration curve and to quantify the temperature with this. So I wouldn't directly transfer use this line to transfer to a temperature, but for sure there is probably some modest temperature decrease. But it seems to be certainly not significant when we compare to the whole variability in the record. So to summarize this, what we got from our data from our Speleothem is that we have a significant local environmental impact, mainly by probably on the vegetation and also the soil conditions. But from the oxygen isotopes, we see only a small regional climatic signal. But maybe our site is just not representative for a regional or global climatic signal. So we have tried to find more about this and try to find a link of our record to the Greenland ice cores, and to tell more about the size of the eruption and to synchronize the chronologies. It would be, of course, important to find a volcanic spike in the ice that can be associated with the Laacher See eruption. So, as I said previously, there have been some candidate events in Greenland, which are plotted here in the upper panel. So these are all northern hemispheric eruptions. So the northern hemispheric deposition towards up is larger than the Antarctic deposition rate, but large enough that the sulfur spike is found in both Greenland and Antarctica. So all these meet the emission constraints of a northern hemispheric eruption with a minimum volcanic stratospheric sulfur injection rate. And if we compare the age distributions of all these candidate events, we find basically only one, this we call V7 at 12, 9, and 4 BP, that has a significant overlap with our with the age distribution curve of our Speleothem age. And we also took advantage of our high resolution SIMS oxygen isotope record. So here you see now the full record of the oxygen isotopes. This is, as I said, in near annual resolution over the full record here. And this is now, of course, comparable to the ice core record. We used age model ensembles to do a correlation analysis of the oxygen isotope records under the assumption that the candidate events are coeval with the Laacher See eruption in the stalagmite. So basically, we derived several age models for each of the records, shifted them, and calculated the correlation coefficient. So I don't really want to go too much into detail of the statistics here. But the take-home message from this is that the correlation between the records is maximal for the same event. So if the event at 12, 9, and 4 kiloyears is simulated coeval to the Laacher See eruption in the Speleothem, then the correlation between the oxygen isotopes is maximal. So, and this is what we would expect it to be, because the atmospheric connection between from the North Atlantic to Greenland and to Central Europe is very quick, and this is what we would also assume, what we have also seen in other records. So what are the implications of this? So on the one hand, so both analyses suggest that so the correlation analysis and our age distribution analysis, that V7 is the most likely event for the Laacher See eruption in Greenland. So this would tell us that the stratospheric sulfur injection rate was relatively small. So you see that this event is quite small, much smaller than, for example, this earlier or this later one here, that is much younger, but much larger in terms of sulfur injection. But basically, we think that this would agree with the weak signal that we see in the oxygen isotope record from our newest data in the 1 or 2 years after the eruption, that there's only a modest cooling effect, and that the cooling is not very outstanding in terms with relative to the whole record. So we think that the climatic impact of the Laacher See eruption was very, very limited. Lastly, I would like to say a few words about the implications if we're of the synchronization of the different archives. So if we use the Laacher See eruption to synchronize all the records, so we have different lake sediment records, we have our Speleothem record, and we would then also have, if we agree that the 12994 event would be the Laacher See eruption, then we could also synchronize the ice cores on that time scale. If we would do that, then all the records would look like this, and that would indeed mean that the Central European and Greenland ice core records would be synchronous. It would also mean that the onset of the younger dryas in Central Europe would be indistinguishable from the Greenland stadial here, and and that of course means that abrupt changes in the North Atlantic propagate really rapidly into Central Europe. So as my take-home messages, I would like to say that I hope I could show you that speleothems can be excellent recorders of volcanic eruptions and their local and regional environmental impact. So when we produce such records, they can be really great to synchronize climate records and such precise and accurate and synchronized chronologies. So we need such efforts to analyze the timing and evolution of events within and also between archives. So I think you had all the link to that paper that we published earlier this year, and I'm happy to take questions. Yeah, thank you.